let's start. So I'm very excited to be here today. My name is Mark Anderson. I'm the CEO of SNS and of Pattern Computer and the chair of FIRE. And I'm here to talk about the influence of biology in chip design, which has to be like close to my favorite idea of all time. Not my idea, by the way, which is why we're here. And I'm here with Carver Mead, whose idea it really was, who is a scientist, engineer, and he is the Gordon and Betty Moore Professor Emeritus of Engineering and Applied Science at Caltech. And as you all already know, if I started doing his bio, we'd be here all night just doing that. So you can look him up on Wikipedia somewhere and learn for yourself. But the exciting thing, I've gotten to know Carver just a bit over the last few months, and what a treat. And the exciting thing for me, or anybody I think in computing, is that Carver really is that guy. I mean, if you want to be in touch with somebody who's there from the beginning till now and saw it all and did it all, Carver is that guy. So but that's not why I asked him to join us. I asked him to join us because long ago he we'll find out how this happened, but he got the idea that biodesign and biologically informed design was very important. And that was not true for every chip designer, I don't think. I'll find out today if that was, but certainly for Carver it was. So Carver Mead, welcome.
Thank you.
Glad to have you with us. And I'm going to try to, we may get a little technical here. I'm going to try to keep things below the 200,000 or above the 200,000 foot level most of the time. Let's start with a really basic question. You have done so many things in your past, in mostly a chip design, but also in lots of other related technology designs. In all that sweep of designing and inventing, is there a single category of that work that you are most proud of or most excited by?
Well, it was all fun, but there is a path through it that's relevant to what we're talking about. So it'd be fun to share that. I started my research with electron tunneling in solids.
Okay.
As you know, electrons, if you put an metal contact on most semiconductors or on two metal contacts on opposite sides of an insulator, well, there are no current flows. And then you think about that a little bit, and well, the electrons are waves and they have wave function. And if you have a electron wave function that can propagate, then electron current can flow. But the insulators and the semiconductors have a band gap. And what does that mean? Well, a band gap means it's a region of energy where the wave functions don't have a propagating solution, but they die out with distance exponentially as they go into the material. Well, if that's true, you ought to be able to make the material really thin, and you ought to be able to see current coming out the other side, and it ought to go exponentially as you make things thinner. So I got fascinated by that. It's a great way to do quantum stuff on a bench, right? So I started doing that, and it was lots of fun, and I did it on semiconductors and insulators and figured out lots of stuff. And one day in 1965, I was consulting for Gordon Moore. I'd take a day a week and go up in Silicon Valley and hang out with Gordon and his people. And one day I walked into his office and he said, "Here, what do you think of this?" It was in 1965. And it was a sketch of his first Moore's Law plot.
Oh, really?
And he said, "What do you think of this?" And I looked at it and I said, "Wow, that's neat." And he said, "You're working on electron tunneling, right?" And I said, yeah. He said, "Well, doesn't that limit how small you can make a transistor?" And I said, "Yeah, it certainly does." He said, "Well, how small is that?" Well, to get all the way down, it takes years of working, but you can make some rough estimates. And by the time you get down to tens of angstroms, things get to where they're tunneling, and it does limit how small you can make these things. And so I made some rough estimates, and it was way, way far away, orders of magnitude smaller than anybody was talking about. So I started thinking about that. And the more you think about it, the more you think what that means is we're not going to design things the way we design them now. People were drawing the layouts on pieces of mylar and cutting ruby liths to make the masks, and it was crazy. It was nuts.
Get your ruler out.
So I had to figure out how to automate that process, and it was just a bunch of figuring out, but came up with this much more organized way of designing large scale circuits, and started teaching courses about it, and then working with students and colleagues on designing things that were as many transistors as we could get on the size chips we could do at the time, which are tiny by today's standard. This was late 60s, early 70s. And then we started thinking about, well, if you want to do computing, most of the hassle, the cost, was I had to think about what is the cost? Well, there's three costs. There's a silicon area, there's a time it takes to do an operation, and there's the energy it takes to do an operation. So it isn't just one cost. So you have to figure out how you trade those things off, and are there optima in the space, and so we did some of that, and you get to thinking, this is a medium. This isn't a thing here and a thing there and a thing somewhere else. It's a medium. You're working in this wonderful, wonderful medium that's growing, that you have what felt like an unlimited amount coming towards you, and you had to find ways to do good stuff with it.
Right.
Glorious time. And we figured out ways to think about optimizing it. And one of the first things that hits you is that those costs, the time, the silicon area, and the energy, are all in standard computer design. They're all tied up in just shuffling data from one place to another. And it's the most inefficient possible thing you can do, is to make a standard computer out of a beautiful piece of silicon.
There you go.
And so we started making, pipeline things so that the data would move through the computational stuff and come out the other side. And there were very efficient ways of doing that. You could get a huge amount of computation for a very small amount of energy and not so much silicon area. And we had grad students that did theses on various ways of doing that. But as you think about it, we had no existence proof for a system that worked that way.
Yes.
So the more you think about it, the more you think, there's got to be a fantastic new way of thinking when you have that medium and you're not stuck with writing sequential code or wiring together logic gates, or it's a medium. And of course it didn't take any serious brain matter to realize that the brains of animals are examples of, it's a very slow, the wetware that you make brains out of. It's very slow, and it's not particularly dense. And it does stuff that we can't touch,
Right.
even today.
Now I want to jump in for a minute, because that's such a beautiful statement. I want to hold that thought. And this is something you and I haven't talked about yet, but I have a biology background, Stanford biology. So what I wanted to inject, and I'll try now, into this conversation is the power of biological evolution in creating near perfect solutions to problems, whether it's duck legs in icy water or whether it's how brains work. Are you comfortable with that idea?
Sure.
Okay, I thought you would be. So by borrowing from biology in any way, what you just said about the brain, of course, right? Because if there's some way for us to learn anything from evolution, the chances are it will be more efficient as an engineering model than go again, go 3 times.
Yeah, there are lessons from biology that you don't have to know all the details to get to realize that there are efficiencies to be had just from simple things. Like the first thing you notice is that biological systems, let's talk about primate and mammals, but just because we're more familiar with how they work, being one. The intelligence isn't all stuffed in some data center someplace, and you have little tiny, paths back to from getting inputs and stuff like that. The intelligence is pushed out all the way to the sensory inputs, and it's pushed out all the way to the motor outputs. And all of that stuff is part of the intelligence. It isn't like there's some central thing, and they're finding this out gradually the hard way, trying to make self-driving cars. And they're just beginning to realize you've got to put intelligence out where the sensors are, and put it where the feedback in the motor systems and all of that. And that's how you asked me how I'd gotten interested in the retina. Well, the retina is literally a piece of the brain.
Extension of the brain.
That's out behind the lens.
Right.
And there's the sensors, and the processing of the sensors are all part of the brain right there. And that's true all the way down in the animal kingdom, that there's a lot of brain right up in the image plane. So that's an obvious place where you can see. Part of the problem has been, up till present day, that the way the brain works, we don't have any inputs that are like that. I mean, we got great big files in great big memories. That's not anything like
No.
photons coming into your eye. Well, that's how we got back in, the 80s, as you know. One of my students got into the retina, and she did just a fantastic job of figuring out how to actually do that. And to this day, it's a model for what people are doing. And people are now making these things they call dynamic vision systems. And what they mean is silicon retinas
Yeah.
Uh,
We did Carver, we had a year at Fire, probably 4 years ago, where we were looking at the retina, and we had, I think this fellow was the best in the world at photomicrographs of the retina structure,
mm,
electron micrographs, and you could see that although they said it was in layers, right? You have 3 layer, whatever it is, but really there was so much interdigitization between them of so many different types of connections that it was just a forest of stuff going on.
yeah,
And the idea that you could have an incoming artillery barrage of how many photons per second or whatever, and then that this was cutting that down by some, you probably know the numbers, some gigantic factor, 10 to the something, before it even got to the optic nerve.
yeah,
Yeah,
yeah.
amazing operation.
It's fantastic data compression, and it's all event driven.
Yep.
And that's the thing that has just started to get into people's consciousness in the information industry, that things if you're going to interface with the real world, things are going to be event driven.
Mm-hmm.
If you're going to dig stuff out of great big files, then you can do that with great big memories and great big things that paw over memories. But if you're going to be in the real world, it's event driven, because that's what matters. Things that move, things that are different. It's a fantastic moment right now that we can go down to and buy one of these sensors that puts out nerve spikes.
Yep.
And it's fantastic, because finally we have a native source of information in the form biology uses it in the brain.
Yes. You'll be not surprised to hear that I have a bias here toward pattern recognition. And that's intimately related to what you're saying.
Yes, it certainly is. Most people are really surprised when they realize that, all we see and all we hear is carried by groups of nerve pulses. And it's the relative time of arrival of nerve pulses on various threads that carry that code.
Yes.
And if you just think about it for a while, the thing that's marvelous about it is that you can arrange your decoding mechanism so that it can see subsets. Because when you're going down a dark path at night, you're making decisions on the basis of a few photons. And at that exact same system with those exact same neurons are seeing the same trees and the same path and in bright light over 6 orders of magnitude. It's fantastic. And if there's a secret in the nervous system, it's that one.
Well, that's one of the secrets, I think. That's the amplification, de-amplification.
That's the deep one.
Yeah. Well,
because if you try to do that with a computer,
yeah,
you instantly get into an exponential explosion of stuff. And
yeah, right. But I would suggest another one is so I'm back to patterns again, because I want to go a little deeper here for a minute, because I don't know you well yet. I know a bit about your background and what you've achieved. And please correct me if anything that I say during this hour is wrong. Just jump in and say that's wrong. But I think of you as being a very deep science guy who sees things just like you're describing today, and recognizes the potential for therefore for things to happen. And you find the scientific interesting, like tunneling first, and then you work backwards to however that'll benefit a chip or benefit humanity or whatever. Is that a fair statement?
well, it sort of worked out that way.
Well, we'll go with that for the moment. And what happened as chips, I think this pivotal place you're describing us right now is partly in the Moore's Law world, right? Where we're hitting pretty narrow channels right now. And a lot of the future of chip design, I'm thinking, will come from biologically informed ideas and maybe more based on pattern recognition or on how do you restructure, not just for small, but for better, for lower power consumption and for more, I don't think things should be just called nerves, but if it were neuromorphic, you'd say, what can we learn from nerves? And one thing maybe would be, how do they process patterns like you're talking about right now?
Yeah, I think you're right on. And that's why it's wonderful that we have sources of events in real time.
Yes.
From real input.
Right, exactly.
And because until we had that, there was no way to move forward.
Yes.
Because you can't really fake it up very well on a computer.
Right.
And we really had to get to where we had real-time stuff.
When you're saying this about events, which I agree with completely, that's on a micro level. That's an individual event, that photon in the dark you're talking about almost. And when I think about patterns you're talking about the connection to the physical and the compute, I think, and I am too, but I'm thinking about the patterns that are endemic, or that's the wrong word this week, but that are inherent to nature. And therefore, having a pattern recognition detection system or computation system isn't just another idea. It actually is perfectly married to the nature of the problems and the world with which it is connecting.
Well, of course, that's why we're able to do it.
Right.
Because, it's perfectly matched to what's in the world. And yeah, and the part that's been missing is it's spatial temporal patterns, not just spatial patterns. So, these systems can do a great job of face recognition, but when you do the time axis with it, now the richness of those patterns, the spatiotemporal patterns, is fantastic. And I'm just very pleased that people are starting to really go for that one. That's
it's still a big, hard problem for a lot of folks.
Yeah, and important problem.
Yeah.
Like, we might actually be able to get self-driving cars if we got good at that.
Something even better. Yeah, that's right.
Yeah.
Well, so you did a lot of work with senses, and I think senses were a little bit of an occupation, not even an avocation. They're an occupation for you. You looked at hearing. You did very early work in cochlear mimicry, and built devices that actually were hearing assists. And the same with vision. You did that, and you look at the Retina, and you built devices based on visual assists, or designed them. And you've been involved in companies that do that. You built the, I think everybody knows this, but am I saying it right? Foveon chip?
Yeah.
So in doing all that, did you go for those inspirations because they were by themselves inspiring, or because you had it on faith that by doing that kind of biodesign, you could reach much higher?
I can't, in my own mind, separate those two motivations.
Okay.
I just can't.
That might be the answer.
It's everything you said is true, except the work was really done by my grad students, who are really, I've had some fantastic grad students, and they have done wonderful work. And you can't if you want to learn about something, at least for me, I've always told people, I can't understand something unless I can build it and make it work.
Mhm.
Because I can theorize all you want, but when it comes right down to it, if I can't make one work, I don't understand it.
Yes.
And so if you're going to make a event-driven computer, they call them spiking computation today. And there's a bunch of people off doing it. It's great. And even Intel, of all people, went and made this Loihi chip that is event-driven.
Surprising.
Yeah, it's great. It's great. I think
Out of character.
marvelous. You know, it's a completely different mindset, and using it, there's going to be a completely different. And you spoke about, how do you program a thing like that? How do you think about it? How do you organize that? It's and of course, part of the answer is it learns. And we spent quite a bit of time thinking about how a thing like this would learn. And there's still people doing good work on that. And more people now.
Yeah.
This is a great time. I mean, it's a great time that there's now support for the things that we had this dream of doing, and having to make all the little pieces just to get things to interact with each other.
Right. So more of my bias. So the were you aware of the True North chip when Dharmendra Modi was building that?
I didn't know about it till it came out, because I had been away from this stuff for a long time because it didn't feel like it was going anywhere.
Right, but you know what it is now.
Oh yeah. Well, it got that award that was named after my student that did the Retina.
Okay.
Yeah. So
that, and then the Air Force Research Lab took over that whole project, of course.
Okay.
Can't buy that anymore. But the idea of a pattern recognition processor, a PRP, I call it, which Dharmendra, I think, felt that was a true characterization of the True North chip.
Mm-hmm.
And you would know better than anybody. Do you see are there more of these things coming down the highway?
Oh yeah. Kwabena Bun at Stanford has done some very nice work on
Spiking
that kind of computation.
Yeah,
right. He continues to do that, and it's his latest stuff is really neat. And there've been other things coming along. There's a group down in Atlanta that's doing really nice chips that learn, and there's a group in Zurich that is doing in fact, they really drove this spike-oriented retinas.
Is that at ETH?
Yeah, at ETH, yeah. Shichi Liu and Toby Delbruck there have done really great stuff. Continue to do really great stuff.
Yeah.
And Christoph Posch has a company now that makes one of these things that's extremely aggressive.
Cool.
High performance. There are lots of good stuff going on, really good stuff, just in the last few years.
Right.
And it is interesting that these two ways of thinking about neuromorphic stuff, that and the backpropagation stuff, which started out as just a software thing. Mm-hmm. But then, regular computers are really lousy at doing it. So they had to get better silicon and better silicon. And now the whole thing is coming together to where, yeah, you're going to have to make silicon so it'll work that way. And so I think that we're at a singular point in history.
I agree. So I want to ask you a question about what you just said. If we look at the run of the history of chip design through today, and then I think we're agreeing that pattern recognition processors, things like that, what you're talking about right now, are some of the future types of designs we'll see. One of the things that occurred to me that was not obvious to me until I actually had a chance to really think about it was that for most of the last few decades, the game was really about 8086 smaller channels.
Yeah.
Right. And so
if you think about it, what was happening is we were working all the way back into the early 70s on all of this parallel processing and how you pipeline things and made the energy optimize things. Nobody did that.
right.
And the reason was very simple, that if you had a design, an FPGA or something, and you had competitors, if you just shrunk yours down, made more memory, more processor, and put it on the next process, you could beat the guy who was doing a better job of overall system design. And so it turned out that the guys that just went with Moore's law,
Yeah.
no new ideas, just make it bigger, put it more on a chip, and sell it with the latest process.
I think for the audience, for the three people who don't have any idea what Moore's law is, would you like to give them the sentence?
Oh, Gordon Moore drew this wonderful plot, which is the number of transistors on a single chip as a function of the year. And it was going up and doubling. In those days, it was doubling every couple of years. And then it's still going pretty good.
Yeah.
But what's happened is finally people are starting to be more clever because they can't just rely on the more transistors because of the process. Now they have to start thinking.
Yes.
Well, this is wonderful because, it's been there all along. And these were the problems we were thinking about in the 70s.
Yeah.
And nobody give us the time of day because it was, you beat the competition by just scaling.
Yeah.
And so now that you can't do that anymore, people are getting more and more clever. And that's a good thing. That's a really good thing.
So that's exactly where I was hoping we would end up on this particular moment, is that in the future, not just the idea of things being more pattern-like, but I think, and tell me what you think, I think that software, which, by the way, the United States tends to be pretty good at,
Absolutely.
maybe better than anybody else, the trend will be to take important pieces of software that are somewhat, not entirely general, but somewhat general for a problem, kind of like TensorFlow was, and put that into the chip design, so that software excellence leads to new chip designs. Does that sound right?
Well, that's been the history. That anytime you get something that gets done over and over again, somebody finds a way to make a chip out of it, and then that becomes an accelerator.
Yeah, right.
And your computer has a whole bunch of computers in it that are specialized for. That's been wonderful. People don't talk about it, but actually that's where a lot of the cleverness in chip design has gone, is into the special little things that have to go like a banshee and they can't cost too much. And so yes, absolutely. That's been the way it's evolved.
Yeah. And does it feel to you like we're accelerating more toward that North Star? Does it feel to you like that's where we're heading? More and more?
the thing about the process is that it has to pay for itself as it goes.
Yep.
And that often takes longer
Mhm.
than if you could go straight.
Yep.
But it doesn't happen that way very often. And I think the reason is that taking one step forward, a bunch of people can do that in parallel, and there are different steps they try, and some of them will stick.
Mhm.
If you try to take a big one, supposing that one doesn't work out, well, you've just blown all your money.
Yeah, you lose wrench.
So the both biological evolution and the commercial evolution has gone by the little steps here. Once in a while, you get a big one.
The invention of the eye.
Yeah, like where Alex went off and did his brute force, more memory, more GPU, more images, and just brute force it. And that was a wonderful, that scale itself was what was missing.
Right.
And none of us knew that. And we'd been working for years on back propagation. It's the same back propagation. There's little tweaks here and there. But the nature of the scaling was not evident to any of us. And that will almost certainly pay in the biorelevant kind of computation. There's probably a scale where the nerve spikes and that kind of recognition that goes with pulling out those subsets of ordered nerve spikes. There probably has to be a scale to that before it, and maybe we're getting there now with bigger chips that can look at more of it, and it could be that lesson we've learned in the software side plays in the bio-inspired hardware too.
It could be. I have a friend who spent his life on nudibranchs, a marine animal, and they this giant nudibranch that had only 8 nerves in it, but lots of synapses and things.
Yeah.
And just with 8 nerves, it was able to like hunt, run away, mate, a bunch of things.
Yeah.
So not just the number of nerves, but obviously the organization, the emergent properties of nerve design and connectivity.
Yeah.
Right?
Yeah.
How that happens.
Absolutely.
In the structure.
Well, of course, a lot of it happens by built-in pattern, but a lot of it happens by learning as it goes.
Yes.
And it's the combination of those two things that are the magic. No one by itself would get you there.
That's right. When I think of a baby's brain, you probably think about this all the time, but the baby's in its mother, and then it's born. And if you ignore the first 9 months, which you shouldn't do, but do that. And then here's this biocomputer. It doesn't know whether it's going to be hearing Russian or English, right? It doesn't know whether it's I got a musician for a father or a marksman, and all the pattern recognition that has to go into the structuring of that new biocomputer just to get started. What is a finger, right? What is a finger?
Yeah.
Then after you get that basic stuff going, it's incredible how fast that thing must be learning and restructuring and restructuring and restructuring.
It's fantastic.
Yeah.
That I remember when we were still working on the digital chip design and all of that. We had Marvin Minsky out to give a seminar, and he was in AI, early AI guy, and he said, we took on machine to do calculus, and we were doing a pretty good job in calculus. So we thought, oh, let's backtrack a little and fill in, and we get arithmetic to work. And to our surprise, we found out it was much harder. And the more we worked on this stuff, the more we realized that most of what you call intelligence is developed in the first year of life.
Yeah.
And so that was the big aha for a lot of people, that the things you aren't even aware of are most of the information process.
How fast that biocomputer is growing intellectually by day.
Yeah.
From day zero.
Amazing.
Amazing. I've got to warn our audience, who are probably happy to hear this, that in 5 minutes, we're going to open it up to questions and answers. Looking forward to that. I have one more big question I wanted to ask you, and then that'll probably carry us right into Q&A. You've done a lot of work on both analog and digital. And probably for the younger people around here, they don't even know what analog is because everything is digital. But they're actually have these two worlds, and it's kind of like watching musicians like Neil Young go back to vinyl. I mean, there's an interesting, yeah. So I'm curious how you see analog and digital, both from the perspective of bio, and therefore from the perspective of the future design of chips.
Yeah, it's a great question. And if you think about backpropagation, what they do is they take you have a network, and you put inputs into the network, and the inputs get multiplied by weights and summed up to make outputs that go to another level of the network, and it does the same thing. And the weights are representations of an analog quantity that happen to be carried by a digital number. But the process itself is an analog process it's being faked up with digital stuff.
Right.
So there are huge opportunities, and we've talked before about if you just took something that people think of as a challenge today and do it analog and do it digital with the same sort of technology. The cost to do it that way is about the same. If you cut a lot of corners in the digital, you use really short integers for the weights and that sort of stuff. But the energy use is about a factor of 10,000 less by doing it analog.
Wow.
So that's an interesting thing.
Yes.
And that's using basically what people now call computation in memory. Mm-hmm. So it's basically taking a memory technology and using a little bit of analog processing, and making the memory store analog values, which is, for example, on EEPROM technology, you can store analog values very nicely, and you can tune them up and down. So it's inevitable that people will start doing that. Unfortunately, it's been driven out of our educational system.
Yeah, right.
I'm partly responsible for that.
Oh, shame on you.
Doing the digital stuff. Well, digital stuff is fun, and I still enjoy designing digital stuff. But the combination of using analog values, that's what the nervous system does. It has these digital spikes. They're digital in amplitude and analog in time dimension. Mm-hmm. And that's a wonderful combination.
Wow, I hadn't thought of it that way. That is really cool.
Yeah.
They're digital in amplitude and analog over time.
So that's where the analog dimension is. And in the nervous system.
Yeah.
And then locally, there's analog processing in every neuron and the neurons around it.
Yes.
So it isn't one or the other.
Right.
This is and the nervous systems of you and I use both, and we're going to want to use the best of both in future technology.
I don't doubt that for a minute, but I do think that the comeback of analog is important, and partly it's the idea that I don't think that nature is digital in a way. I suppose quantum mechanical people would argue all night long about this, but it seems as though there's an awful lot of analog out there that we could mirror, and by doing that, have low power computation of them.
Yeah. Well, so far, there are no digital circuits. They're analog circuits which we hook up, and they have gain, so they drive them against the stops, and they call that a digital signal because it has gain, so it restores the signal every stage. And that's what's digital about it, is that because it keeps the errors and the noise from overwhelming the signal. So that's what's digital about it. But they don't bother to tell students that that's what's digital about it. It's an analog circuit that you use in a particular way. And if you're really going to keep yourself out of trouble, you better understand the analog nature of the digital circuits too.
All right, I could do this for 5 more days, but we'll just have dinner together soon. So I think we have an MC in the background somewhere who will save me from being the questioner, maybe at 7.
Yeah, and we'll just dive right in here. There's plenty of questions, including, so Shalev got in there early with a very early question, but then had a number of others. Shalev, do you want to pick maybe kind of some of your stuff probably got covered a little bit and some didn't, but do you want to pick a top question that you want to ask?
Yeah, I've got like 20 written down here, like this whole time, by the way, but I can't say on. Hey, Mark. First of all, thank you. That was really good.
That was good.
That was great. For me, as somebody in the deep learning space, that was really great hearing about the chips and then hearing you go towards deep learning too. It's just great. There's actually something I wanted to mention and ask you about. Right now, neural nets are kind of in a similar stage to something you described, I think, in that you said, people were making chips smaller, right? And that was kind of beating out just the smarter design of the chips because they could just make it just smaller, right? Neural nets right now is kind of similar too, because people right now are just making them deeper and spending, hundreds of thousands, if not millions of dollars, think OpenAI, GPT, right, on training these massive neural network models. And not many people are actually rethinking or going towards a smarter design of models. And there's a key issue here, and this is something I think about often, which is that neural nets have co-evolved with these little bells and whistles for the past 10 years, like adding a batch norm layer or adding whatever, all these little things, these different optimizers. And so the current form of neural nets that we have is super co-evolved to be optimized with our current bells and whistles and tips and tricks, right? So when somebody comes with a smarter method, or that might be smarter, it doesn't have that 10 years of co-evolution with those bells and whistles. So it's gonna do worse. And so you can't even convince people to go towards those smarter designs because it needs another 10 years to get. So how do you overcome something like that today?
That last clause there, Shalev, it won't do worse. It'll do better, but it won't have that ecosystem yet.
Yes.
And I think Carver probably has a better answer than I just gave you.
Well, I think that's a great question, a great observation, actually. It's always been true that the entrenched ecosystem is resistant to innovation. That would change the way you think. It's true of our educational ecosystem. It's true of our commercial ecosystem. So it seems like what really happens is there's some combination of potential in the technology, and somebody finds a little foothold in a commercial app. And that was why I'm so excited about the event-driven visual sensors. They're not a big market yet, but it's enough to get it going. And then as you say, all the bells and whistles, well, now we've got some new bells and whistles. People will find ways to use those to do good stuff. And then that maybe encourage somebody to do an event-driven thing that will take those events and do something with them really clever. And it's good that we have silicon foundries that can fab your chip once you've got a really neat design. And so, yeah, but you're right. It favors the status quo. It needs to be. It takes not only good idea with a big potential, but it takes a lot of belief and guts and work in the trenches.
We had the experience of having Jensen Huang on stage at Fire back when he thought he was in the gaming business only. And we have it on tape on whatever, on chip somewhere, where I was doing an interview with him. And I suggested that he turn, we call it XY computing, that he turn his chips on the side and become a processor, a CPU, instead of a GPU. And it's a beautiful moment, at least in Fire history, because that, of course, that caught on. That worked out. Go ahead, Evan.
So Rick Lefebvre, you had a question kind of asking for insight about a specific.
Yeah, Carver, hi. So back in the 80s, when I was running the labs at Tektronix, you and Lynn Conway started a revolution convincing mere mortals that they could take their software algorithms and stick them onto chips.
Yeah, that's
All
true.
of a sudden, we had graduate students and software engineers using MPCs to create chips. And tell us about that insight and what was going through your mind back in those days.
Well, it started out as I described, that I wanted to design those chips myself. And I watched the way Intel was doing it, and they were drawing them by hand on Mylar and tracing it on Ruby Lith to make their mask. And no way I could do that. So I had to find a way that I could write code to do the layouts. And it turned out that worked out. And I was able to do my first chip and get it to run. And then, of course, the students all said, hey, that's really neat. Will you teach a course in it? So that was 1971, and started teaching students. Well, when you teach students, and we would get the chips fabbed, and they would come back and they'd make them work. And when a student has had that experience of really doing it every step themselves, you can't tell them that it can't be done. So they would go out into the industry, and some of them would say, hey, why don't we make a chip to do that? Oh, you can't do that. No. Well, I've done a chip that did something related. And once in a while, they got the okay to do it, and then it took off.
Those were heady days, and it's software scales. Writing it as programming scales much more than drawing lines on a piece of paper.
Absolutely, and it is so obvious. But boy, you see what happens is just like the young man described, that there gets to be a set of things that are the way it's done. And they're all supported and documented and talked about and taught in the classes and all of that. And when you're doing it a really different way, none of that's there. And well, so you have to,
Those were heady days, thank you.
Yeah.
A lot of fun.
So I think we have time for one more, Carver. This should end on kind of an interesting, sort of a bang, I think. So David Brin, you had a question about actual artificial general intelligence and claims about reaching it. And are you still with us?
Yeah, unfortunately, I switched to my laptop. The camera's not working. But Carver and Mark, that was absolutely phenomenal. That was terrific. My question is, as you might expect coming from me, a little bit into the future, do you have an opinion about how we'll be able to tell? Because it's inevitable very, very soon that the emulations of pretend AI are getting so good that even the concept of the Turing test starts to come into question. So do you have any opinions about when realistic emulation becomes actual artificial general intelligence? And will we be ready with any kind of a response when these entities or the teams that made them start claiming they've crossed that very vague line? Should we be ready?
Carver?
Well, I can tell you my own response to that has been, when people ask me about it, I always say, don't hold your breath. And it's not because the things that are going on with deep learning are not impressive. I think they're wonderfully impressive, but it really reminds me of the arguments about letting kids use calculators to do math. And it's a confusion between conceptual things and table lookup.
Yep.
And these deep networks are wonderful, fantastic lookup tables. And when you think about them that way, you realize that they're like a calculator for a much bigger space. And that makes the human beings that work with them much smarter. So we need to be able to, it's the next step. I remember when we got the fast Fourier transform. And that literally transformed how we could do digital signal processing. And maybe they didn't want the kids to do it because it was too simple or something. But I think we should welcome the availability of these wonderful, it's the new encyclopedia. I remember when I was a kid, I used to love looking stuff up in the encyclopedia because you could, almost anything you could go find stuff about. And so I think that's, so what if you want to then think about what comes of that, it means we have to be smarter about how to use these wonderful lookup tables.
And that was perfect. May I add one more sentence, or I want to do a little plug for FIRE here in a minute, but I think Carver, I think that neural network, when people say AI today, I did a little test once a couple years ago at a DOE meeting. 99.5% of the people, maybe 100, thought that you meant neural networks. Right?
Yeah.
And we could, in Marvin Minsky's name, we could say, well, there's actually more to this story. So I've started using AM for advanced math because it's not just neural networks. And neural networks have really big problems, like the black box problem, can't see inside of them, how they did it, why they did it. And declining return on investment, the more you go, and somebody pointed that out today. So these things, which are powerful, I agree with you, but they're limited. And they're very, very far away from anything you would describe as general intelligence. They're not even close. They're very good at predictive, not creative thinkers, and not big discoveries. So that's my personal view, but I'm a battery computer guy. I would like to, Evan, as we close, I'd like to mention that we have Advanced AI Day or Advanced AM Day all day on Wednesday. So this conversation will flow naturally into that. And we also have Larry Smar with us tomorrow, talking about very large scale networks and exascale computing and how that works, including on Elon's Tesla car network. So that'll be fun. And all in all, oh, and then we have the big reveal of Carver. You got to come to this on Wednesday at 5 o'clock. There's a pattern computer reveal of a top secret project. It's been 3 years in the making. Real XAI, real explainable AI that works on neural networks as well as on our own stuff. So more to come, but it's none of it's advanced, none of this AGI stuff. None of that.
All right. Well, on that note, thank you, everyone. It's been a wonderful first day, a wonderful panel, or centerpiece conversation, and we are now moving into the slightly more relaxed part of our day.